Hey everybody, final section of Unit 5, we're going to do some probability, which in all likelihood is stuff you've already learned in the past. I don't know how far back into the distant past. So you might remember all of this. So I'll probably move pretty quick. And just let me know if there's anything I need to kind of clarify or elaborate on or go over again or whatever. Let's start with simple probability. The textbook definition of the probability of an event. And don't be surprised to see this notation, here and there where like they use the letter P and then they put something in parentheses, whatever the event is, so you might see like a P and then in parentheses like rolling a 6, or it might just say 6, I don't know, but this is fairly common notation to give like the shorthand of like the probability of whatever event E. Anyway, the textbook definition is the number of favorable outcomes over the total number of outcomes. Well, okay, total number of total. That was a little redundant, so I don't know if you want to write the word total again, but maybe that's just kind of like extra emphasizing the point that it's the total outcomes on the bottom of the fraction. So it's like a ratio, it's a percent, it's a fraction, whatever. The number of ways to win or favorable outcomes over the total. And I don't want to go too deep down another rabbit hole here, but if the question called for finding the odds of something happening rather than the probability, that is a different fraction. It's a different ball game. Maybe we'll go over that, as like an aside in class, but the probability, it's a fraction where you have the number of favorable outcomes or the number of ways to win out of the total. So the probability of rolling a 6 on a regular die or dice is 1 out of 6. There's one way to win out of 6 total possible outcomes. And I'm also going to be including, I guess, the decimal. I think just the decimal, not the percent. So that's like the decimal. Looks like I eventually rounded off. But you could also say this is a percent of like about 16.667%. Because fractions can be converted to other things like decimals and percents. The probability of rolling a 5 or a 6. So don't get confused by the word or. Don't overthink it right now. You're still just doing one roll of the dice, but now there's 2 ways to win. There's 2 favorable outcomes out of the 6, which of course reduces to 1/3, and the decimal would be that, and then of course you could talk about the percent being about 33.3%, Maybe you know all about a deck of cards. But if you had like a standard deck of cards, the probability of drawing an ace, again, like you might not even know how many total cards, how many of those total cards are aces, but 4 of them. You have the ace of hearts, ace of diamonds, spades, and clubs. So 4 out of the 52 cards are aces. That reduces to 1 out of 13. Which of course can be made into a decimal or a percent. Probability of rolling snake eyes. Okay, at least we're getting a little bit more interesting with this next example. Probability of rolling snake eyes, that's rolling 2 dice and getting both of them 1s. All right. Now, I have to remember that at this point you've already looked at section 5.6, of course, which was about the counting principle. So knowing about the counting principle, especially being, taught a little bit about the counting principle, you should know that there are how many different ways to roll 2 dice. Like, how many different outcomes are there possible rolling 2 dice? Okay, that's going to be 6 times 6. So there's 36 total outcomes that could happen when you roll a pair of dice. And only one of them is snake eyes. Only one of the 36 possible outcomes is a couple of ones. So 1 out of 36, which is that decimal. So can you imagine being in Vegas or, Erie, Presque Isle, and making a bet that you're going to roll, like at the craps table, I think it is, and you make a bet saying, like, I'm going to roll snake eyes, and then you actually roll snake eyes? That's a huge payoff, in relation to what you bet, of course. But again, let's just stop right there. I don't want to, again, because now I'm actually getting back into the whole world of odds, along with, I guess I just want to stick with probability. I mean, they're very tightly connected, but now some examples. An experiment. Feel free to please do these, like pause the video if you have to, and try to figure these out on your own without my help, But an experiment consists of rolling 2 fair dice and adding the dots on the 2 sides facing up. Oh, that's how it works. The 2 sides facing up. I didn't know that. But anyway, we roll 2 fair dice and we're going to add the dots. What is the probability that the sum of the dots is 6 or 9? Okay. So, once again, there's 36 total outcomes. I think here a pretty good plan would be figure out how many of these outcomes would sum up to a 6 or a 9. And again, how would you do that? I'm thinking we literally just list them and count them. So you could do a 1 and a 5, or, okay, you could end up with a 5 and a 1. These are 2 different outcomes. Just like 2, 4, like one dice becoming a 2 and the other dice, or die, becoming a 4, is different than having a 4 with a 2. That's different. Of course, 3 with a 3, you can't duplicate that. That is like one single outcome. And then these other ones. So bottom line, that means there's 9 total outcomes of the 36 that result in getting a 6 or a 9. That's a 6, a 6, a 6, a 6, a 6, 9, 9, 9, 9. I'm pretty sure those are the outcomes that end up with a 6 or a 9. Now this reduces, it's a decimal. Oh yeah, like I said, the counting principle. So again, pause the video if you need to jot that down and you need time to do that. But number 2, I'm moving on. Following balls are placed in an urn, because that's what you put in an urn, colored balls of, some kind. But there's 4 red, 5 yellow, 4 blue, and 5 green. Amazing. 1 ball is randomly drawn from the urn, as one does. What is the probability that the ball is either yellow or green? So in this situation, where they use the word or, and it's really just like one pick, you can add these yellows and greens together to become 10 total ways to win. Okay, the 5 yellows and the 5 greens, that means there's 10 colored balls that are either yellow or green. But there are 18 total, so it's like 10 out of 18, which reduces and or becomes a decimal and maybe even a percent. Okay? I'm expecting this to be very, very easy for you guys to understand or remember from your days past. But again, even as I say that, you should really, really, really consider doing these first, like pausing the video and trying these just to test yourself, if nothing else. So again, like, feel free to pause the video and try these first. But Monica has a jewelry box of earrings. The box contains 2 pairs of plain gold, 2 pairs of gold earrings with diamonds, 6 pairs of plain silver earrings, geez, Monica, and 3 pairs of silver earrings with diamonds. Oh, geez. Might have to read this again here in a minute, but if she picks a pair of earrings at random from the box, what's the probability that she picks a pair with diamonds? Okay, I think like these had diamonds, and another kind had diamonds. The bottom line is you add the ones up. There we go. So it looks like there's 5 total. Well, I guess I don't want to use the word total willy-nilly, but there's 5 favorable pairs of earrings that have diamonds, and there are 13 total pairs. So if she just picks a pair at random, looks like she has a 5 out of 13 chance of getting that, and of course that can be made into a decimal, but so nothing crazy, just a lot of words that you might need to just read carefully to make sure you're coming up with the correct fraction. I think you understand the whole concept, but a lot of reusing of the words here that might confuse you. Number 4, 21 students at Hunley Elementary made the honor roll. Good for them. As a reward, the principal is sending one of its honor roll students to space camp. Each student's name is placed on a piece of paper and then placed in a hat. One name is randomly drawn from the hat. If there are 8 boys on the honor roll, what is the probability that the name drawn is a girl's? Whoa, okay. So again, just don't let all the different wording confuse you. Just remember the bottom line. Probability is the number of favorable outcomes out of the grand total. So what's the grand total in the hat? Like, we're drawing one name from a hat. How many total names are in that hat? 21. We want to draw a name that is a girl's name, or we want whatever, and if 8 of them are boys, that means, 13. I'll just showing you where it came from. So 13 out of 21, because there's 13 girls out of a total of 21. And so there's the decimal if that's what you need to have. But yeah, okay. More examples. 64 chips are numbered 1 to 64, placed in a barrel, because that's what you put in barrels. You put numbered chips in there. 1 chip is randomly pulled from the barrel. What is probably the number on the chip is? Okay, wow. I don't know why these examples make me nervous. Maybe it's just a matter of like, can you literally subtract from 64, or do you got to be careful how you count? So like if you're if you're including the chip that's labeled 21, is it as easy as just subtracting? I don't think it is. I think you got to be careful about how many, you might want to like actually count and like 21, 22, 23, 24, 25, 26. See? What you actually end up doing is subtracting 20. I hope you understand the bottom line, doing this math. I hope you understand why this is technically the math and not 64 minus 21. But so it looks like there's 44 favorable chips out of 64. That, of course, reduces and becomes a decimal or a percent if that's what you need. Okay? So this is a good... I'm glad I included an example like number 5. Just make sure you understand why it was 44 and not 45. Okay? Bethany's class took a field trip to Six Flags. Good for them. During the day, Bethany became separated, from her class. It is now time to leave, and she needs to find the right bus to get on to go back to school. Bethany attends Washington Elementary. In the parking lot, this is very long-winded. I explanation. In the parking lot, there are 4 buses from Washington, 6 buses from Adams, and 8 buses from Jefferson. Okay. Unfortunately, all these buses look alike. If Bethany goes up to a bus at random, good plan, Bethany. If Bethany goes up to a bus at random, what is the probability that it will be the wrong bus? So now the favorable outcomes are all the wrong buses. So you would do, the Adams plus the Jefferson, and the total you would include all of it. And so Bethany's chances of picking the wrong bus at random would be 7 out of 9, which is that decimal. I might skip this one just for the video. If memory serves me, this is not a perfectly fitting problem for this whole thing, but in the woods there are 5 times as many white-tailed deer as mule deer. If Jacob gets a deer, it fits. It's extra tricky, I suppose, but it obviously fits. It's about probability. If Jacob gets a deer in the woods, what is the probability that Jacob gets a mule deer? How do we set up this fraction just going off of how they said that there are 5 times as many white-tailed deer as mule deer? What is the probability that Jacob gets a mule deer? So there's less mule deer. There's 5 times as many. What are we going to do here? I honestly can't remember what I put behind these boxes, but my thought is to sort of, at least to an extent, maybe a large extent, just use guinea pig numbers. You know what I'm saying? You can just throw in some random numbers that you can find the probability just doing that. Let's say there are 10 mule deer. That means there are 50 white-tailed deer. You know what I'm saying? So, but you got to be really careful about the total. Okay? So, I think this is going to be a 6. Yeah. Because for every one, this is where I get this fraction basically. For every one mule deer, there's 5 white-tailed deer. Which means if you were talking about one mule deer, it'd be out of 6 total. So 1 out of every 6, basically. The bottom line is 1 out of every 6 deer is a mule deer, because that'd be 1 in 5. You know what I mean? 5 times as many. Good problem. But now we're going to get into compound probability. This is where you probably have experience with this, but you might be shaky or flat out cannot remember how this works. Compound probability is when you have 2 or more separate independent events, in a row, together or in a row. And you want to know the probability happening together in a row. Okay, do you remember how this works? Here, the probability of rolling 2 3s in a row. Yes, let me address the elephant in the room maybe, or at least the baby elephant in the room. This first problem, you can totally just think of one fraction, 36 total rolls, and how many of those 36 outcomes would be 2 3s, just like we did snake eyes. I get it, okay? So, but what if we wanted to consider this 2 separate events that each had their own probability? How do you figure out the probability of doing this two things in a row? Here it is. Here's the big concept, the big teaching point that I hope you remember already. You multiply. You might want to write that down in the margin somewhere or whatever. You multiply the separate fractions. Okay, that is what you do when there's separate independent events and they each have their own separate probability, and you want to figure out what's the likelihood of all these things happening in a row, you multiply all the separate fractions. I hope you remember how to do that, multiplying fractions. Now, number 2, the probability of flipping tails and then drawing a spade from a deck of cards, like in a row. Well, what's the probability of flipping tails? 1 out of 2. What's the probability of drawing a spade from a deck of cards? Now, there are 13 spades. Now, that's 13 out of 52. That ultimately reduces to 1 out of 4. So the probability of doing these two things in a row, you multiply the fractions together, and you get 1/8, which is 0.125, or 12.5%, 12.5%. I hope you remember this. That's a lot of people forget this. How to handle like this multiple things in a row probability. All you do is you multiply the fractions together. So some examples that I would encourage you to do on your own before I just go ahead and reveal these answers. In a family of 2 children, excluding multiple births, like twins, you know what I mean? So 2 children, what is the probability of having 2 girls? Assume it's basically a 50-50 chance, which it basically is. But what's the probability of having 2 girls in a row? Well, the chance of having the first girl is 1 out of 2. The chance of having the second girl is also 1 out of 2. You just multiply them together. Okay, multiply the separate. This is 2 events, basically, or at least you can obviously think of it as 2 separate events that each have a probability of 1/2. So you multiply them together. Maria flips a dime 4 times. What is the probability of that she will get at least 1 landing on heads? So how do we do this one? This one is actually a little tricky. That she will get at least 1 head. Yeah, I didn't think this was, well, I guess here's where it is about like compound probability, okay? Having 1 coin land at least, see, the thing that's making this extra convoluted is that it's at least, okay? That means she can have like 1, 2 dimes that land on heads, 3, or all 4. So basically, you could like reverse this and just think of it in this light, that what we're really trying to find is like, what's the probability of getting all tails? But what we're looking for is everything other than that. It's like every outcome other than getting all tails. So what's the probability of getting all tails? Well, that's 1 out of 2 times 1 out of 2 times 1 out of 2 times 1 over 2. But then you would subtract that from 1, because 1 is like 100%. It's like the whole, So it turns out that it is 15 out of 16. Another way to think about this is that there are 16, like think of the counting principle. When you flip a dime 4 times, there are each one can happen 2 times. So counting principle says that the total number of outcomes is 2 times 2 times 2 times 2, and that's the 16. You know what I mean? And 15 out of those 16, you will get at least 1 head. Which means it could go like heads, tails, 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 or heads, heads, tails, tails, or tails, heads, tails, heads, or tails, tails, heads, heads, or you know what I mean? Like you could list all the different outcomes, and if you listed them all, there'd be 16, Tails, 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 heads, heads, tails, 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 tail, you know what I'm saying? 16 total. Anyway, number 3, for Mother's Day, you purchase 3 Mother's Day cards. You address 1 envelope to your mother. Yada, yada, yada. Read this if you want to. Pause the video. The first event, you have a 1 out of 3 chance, and then a 1 out of 2, and then a 1 out of 1. For an overall 1 out of 6 chance that you get all 3 random picks in a row. You know, you have a 1 out of 3 shot, and then a 1 out of 2 shot, and then a 1 out of 1 shot. Because you, like once you pick a card in an envelope, now there's only 2 left to pick from, and then 1, you know. Finally, just a quick little look at the difference between what's called theoretical probability and experimental probability. Theoretical probability is the probability of an event happening in theory, or like never mind. Just I won't. Bottom line is like this is what theoretical probability is, where the outcome is 100% random. Of course, it's got to be like a sterile and fair environment, you know what I mean, where there's no, there's no tampering with the probability, you know what I mean? Like it's got to be 100% random, no funny business going on, and so theoretical probability is what happening in theory. You know, for example, the theoretical probability of flipping tails is 1 out of 2. But that doesn't mean if you flip a coin 10 times, you get 5 and 5, you know. This is what happens in theory, okay? But if you run an experiment, let's see, and well, really quick, before I go there, it is said that if you flip a coin a large number of times, let's say millions of times, even though you'd go on streaks of heads or streaks of tails, you'd eventually even out to like half and half. Okay? So, you know, let's say you actually flip a coin 10 times and the results are 7 heads and 3 tails, which could totally happen, you know? Now, if you flipped it 10 million times, you would just, the more you flip the coins, the more it eventually just evens out to being like half and half. But you do this experiment and you get 7 and 3. You know, then there's actually a thing called experimental probability where you would, based on this experiment, you would say the experimental probability of flipping heads is 7 out of 10, not 5 out of 10 or 1 out of 2. But based on this experiment, I guess the probability of getting heads is 7 out of 10, which I don't even know why we even talk about this kind of thing. But and the experimental probability of flipping tails is 3 out of 10. So just know this term. Know this term and how it plays out. And a couple examples here, I suppose. A spinner was spun, because that's what you do with spinners. You spun them, you spin them. A spinner was spun 16 times. The results are shown in the table below. Got 5 yellows, 4 whites, 0 reds, 2 blues, 2 greens, and 3 oranges. Which colors oh, this is an interesting question. Which colors' experimental probabilities match their theoretical probabilities? How would you figure out their theoretical probabilities? Well, wouldn't it be based on the size of the piece of the pie here? You know, like look at white and yellow. Based on the size of this piece, you would think, in theory, you have like a 1 out of 4 chance, because this is like 1/4 of the entire spinner. You know what I mean? So in theory, you have like a 1 out of 4 chance of it landing in white, just like there's a 1 in 4 chance of it landing in yellow. How about orange, green, blue, and red? Wouldn't that be like 1 out? Isn't this like 1/8? Like, yeah. So if a spinner was spun 16 times, in theory, wouldn't it land on white 4 times? Like, ooh, there we go. 4. And if it should land in red, in theory, 1/8 of the time, wouldn't that mean red, you would expect it to land 2 times? Right? and blue 2 times, and green 2 times, and orange 2 times, and yellow's 1/4, so 4. So which one of these? I mean, this is just kind of elaborating on what I was kind of just saying, you know. That means like 3 out of the 16 was orange. We would have expected there to be 2. So orange did not match. Like the experimental probability was 3 out of 16. That does not match the theoretical. The theoretical would have been 1/8, you know, 2 out of 16. Anyway, I think I've explained it enough. The final answers here are white, blue, and green. White, blue, and green. This last example before we stop. In an experiment, a 6-sided die is rolled a number of times. The results are shown below. So we rolled it a number of times. We could probably figure out how many total, because it looks like we got a 1 4 times. Looks like it landed on a 2 3 times, 3 7 times. We got a 4 8 times, and so on. So look, this did, like, you would think it would be like an even split among the 6 outcomes, but it's not. Like, look, 8 and 8, and this is 3. Woo! Okay, see? So we have like an experimental probability. So based on these results, what is the experimental probability? And again, that means it's based on the results, not based on what should happen or in theory. It's all based on the results of this experiment. So what's the probability of rolling a 5 or a 6? Well, again, it's back to like total number of favorable. So 8 and 5, like this would be the total number of favorable outcomes, and then you would add all of these up to get the total, and so 13 out of 35, which of course you could, you know, convert to a decimal or a percent if you needed to. So that's section 5.7. If there's any follow-up questions, please let me know in class or reach out to me.